design of cloud security mechanisms and secure storage systems. And today he'll be talking about how to provide plausible deniability in storage systems against multi-snapshot adversaries.
Okay, so hi, I'm Anrin, and I will be talking about DataLair, which is a joint work with my colleague Chen and my advisor Radu from Stony Brook University. And I hope by the end of this talk, I'll convince you that DataLair is a new storage mechanism that provides plausible deniability against multi-snapshot adversaries. So before I go into the technical solution, I would like to motivate the problem. And as I've sketched here, these are some of the cool new portable storage devices that we're using. And we end up storing a lot of high degree sensitive information on them, such as, I don't know, social security cards, etc. And of course, one of our goals should be to protect this data from untrusted parties. Now, as common wisdom would suggest then, we can use encryption. We can encrypt our full disk with tools such as BitLocker or DMcrypt, which work with almost minimal overheads. However, trusting only on encryption to provide privacy has certain problems that is summed up by this cartoon, which is popular in the crypto circles, which says the easiest way to break an encryption scheme is to beat the user with the proverbial rubber hose until she reveals her encryption keys or passwords. There might also be situations where your government asks you to hand over encryption keys, and that's not really a problem, and I'm not advocating you hiding information from your government, but this power needs to be used responsibly. So I have pulled out some examples out of the many that I found on Human Rights Watch where this power has been misused and even legitimate users have been asked to provide encryption keys to their sensitive data. So clearly, when you have coercive adversaries that can ask for an encryption key from you, you need something stronger than just simply encryption. And so McDonald et al. In their seminal paper suggested plausible deniability, which allows you to ideally claim to an adversary that you're not in possession of some sensitive information. And now this adversary has to prove with some high level of confidence that this claim is false. Moving away a little bit from the story, I'll describe a solution which was popular for a few years called TrueCrypt. And TrueCrypt was basically a block device level solution which allowed you to create multiple volumes, some of which you could claim to be hidden. And then TrueCrypt would encrypt data from this hidden volume and store it in the free space of the public data. And then you could claim to an adversary that I just have public data and free space on my disk. TrueCrypt was great because it worked with minimal overheads. The problem was TrueCrypt did not provide plausible deniability against what we call a multi-snapshot adversary that can access the user's disk at multiple points in time, and that is possibly after every access. The adversary can then save disk snapshots, file system states, etc., and compare them, and then can detect all the writes that have taken place in between these snapshots. So clearly, in case of TrueCrypt, the adversary would see that the free space changes frequently, which should not be the case if you only have public data on your device. So then our claim is, DataLair provides efficient plausible deniability against such strong multi-snapshot adversaries. So when we started building DataLair, first we wanted to understand what we really need for plausible deniability. We wanted to reduce it to some known security primitives and then implement them as a part of our system and then provably show that we can guarantee plausible deniability. And we identified two indistinguishability conditions, which we have termed as HWA and PAT in the paper. And we show that these two conditions are in fact necessary and sufficient for you to claim that your system is plausibly deniable against a multi-snapshot adversary. I'll informally define what these means. And HWA basically means breaking all kinds of links between a logical address space and a physical address space. So following the TrueCrypt paradigm, example, you have a hidden logical volume and you have a corresponding physical partition on the disk. The location of data on the physical partition is independent of its location in the hidden volume and also independent of whatever data you're storing. And it turns out that Blaise et al. From CCS 2014 Hive, which was the state-of-the-art plausible deniability scheme when we wrote this paper, showed that one of the ways we can achieve this is using a write-only ORAM. And we have also used a write-only ORAM for building DataLair, as I will describe later. The second property we identified also informally means that a device that has hidden data looks indistinguishable from a device that does not have hidden data. So again, following the TrueCrypt paradigm, my disk, which has a logical public volume and a logical hidden volume and corresponding partitions, looks identical to your device, which only has public data. And then I can claim to an adversary that I only store public data on my disk, and I'm only using this for public data operations. Now, using these two properties, then we build DataLair. And DataLair has two clear motivations. The first being, we want to make public accesses as efficient as possible, because it gives you a plausible reason to use this device without any hidden data. It makes no sense to use a mechanism which is orders of magnitude slower and claim that you are using it only for public data operations and you do not have hidden data. And it turns out that this is not even challenging, because we do not need any special security guarantees for our public data. We are not denying the existence of this public data on the disk. The second, we of course want to also speed up accesses to hidden data. And so we designed a new write-only ORAM called DL-ORAM, which improves on the state of the art. So first I'll talk about what DL-ORAM is, and then show how we use it as a black box for building DataLair. So DL-ORAM is a position map-based ORAM for all those who are aware of it. And DL-ORAM has two key optimizations. The first being DL-ORAM stores the position map as an oblivious B+ tree with the same data, and this conveniently avoids recursive position map traversals, which is inherent to most position map-based ORAM designs. Second, and more importantly, DL-ORAM uses a free block finding scheme that allows you to find random free blocks for writing data with constant disk access complexity. We achieve this using an oblivious data structure to store block addresses of free blocks, and this gives us an overall complexity of order log n versus order log square n, which was the state of the art. So I'll discuss how the free block selection works, and I'll refer to the paper for details on the position map. So our free block selection protocol is actually pretty simple. So DL-ORAM creates, for anybody who's aware of Hive and the free block selection protocol there, you can view this as a reverse of that process. And so DL-ORAM builds two sets of constant size, each containing block addresses. The first being the free set. The free set contains randomly selected block addresses corresponding to blocks that are currently free on the disk, and a random set that contains block addresses corresponding to any random block selected from the disk. These two sets are then combined, and DL-ORAM performs a final sampling step from which you get a sample of constant number of block addresses, some of which can be free. If you do end up with some block address corresponding to a free block, you write the data to this location. If not, then you write it to an in-memory stash, and it can be shown that if 50% of the ORAM is free, then the stash remains bounded to a constant size with very high probability. Now, from this slide, I would like to convince you that this mechanism works with constant disk access complexity if we have some mechanism to track free blocks on the disk with constant access complexity. And in DL-ORAM, we achieve this using a oblivious data structure, which we call the free block matrix. And without going into too much details of how the free block matrix works, I'll give you the main takeaways from this. The free block matrix stores block addresses corresponding to blocks that are currently free on the disk. It can be obliviously updated, so it means that entries from the free block matrix can be added or removed without leaking information of what item has been accessed. It will also allow you to uniformly randomly select addresses from within the free block matrix. And both of these operations can be performed with constant number of disk access complexity. Then, using this, we can analyze how DL-ORAM works. And the write complexity for DL-ORAM is just a combination of the free block selection and updating the B+ tree position map, which is a height of log n. So your overall write complexity is order log n. And your read complexity is just due to reading the position map, which is again order log n. So our overall access complexity is order log n compared to order log square n for the state of the art. Now, since DataLair was published, there has been some follow-up work, which I would also like to highlight here. So we had, last month, we were contacted by Roche et al. From US Naval Academy, and they said that they had identified an attack on DL-ORAM and another existing write-only ORAM called flat ORAM, if somebody is aware, based on the fact that the free block selection protocol will select more number of free blocks in the combined set. So we did some follow-up work, which can be found here, to fix this attack. And it seems that there is a simple fix to this, this is our original free block selection protocol. And here, instead of creating a random set, we now create a set of occupied block addresses, and the rest of the sampling step remains the same. In this case, we can in fact show that the sample of blocks that are finally modified per write is indistinguishable from a random sample, or in other words, DLORM generates a write trace which can be generated by a simulator with access only to public information and to random oracles. Again, I would like to convince you that this works with constant disk access complexity if we can efficiently store block addresses for occupied blocks. And since we know how to do it for free blocks, we can use the same trick to store block addresses for occupied blocks. Here again, we use something called the non-free block matrix, can be updated obliviously, and has a constant disk access complexity. Now, using DLORM, then, we built DataLair. And first, I'll describe DataLair Lite, which is a simplified form of our design. DataLair Lite creates two partitions on the disk, the public and the hidden partition, corresponding to a public and a hidden volume, following the TrueCrypt paradigm. And public volume operations are performed without any address translation, while hidden volume operations are performed through DLORM. And by construction, DLORM provides HWA, which is one of the necessary and sufficient conditions. DataLair Lite also works in two modes of operations: the only public mode, where DataLair only tracks public data on the device, and a public hidden mode, where DataLair tracks both public and hidden data. The only difference in access here is when in only public mode, an access to the public data is accompanied by an access or a simulation to DLORM, while in the public hidden mode, access to the public data is accompanied with a real access to DLORM. We also show that these two modes of operations are indistinguishable, and thus DataLair Lite is secure against a multi-snapshot adversary. Now, DataLair Lite, from a security perspective, works because it follows both the necessary and sufficient conditions for ensuring plausible deniability. However, it wastes space. So you have to create two partitions, even though you might not be storing any kind of hidden data. And so we go ahead and we build DataLair, which merges this hidden and public partitions. However, now we have to keep track of two things. We have to avoid overwriting of data, both hidden and public. And we have to avoid visible patterns where hidden data might, where public data might avoid writing to locations which are already occupied by hidden data, thus leaking that you have more than public data on your disk. Now, this is a non-trivial conversion from DataLair Lite to DataLair, so I'll refer to the paper for more details. So yeah, now let's talk about how DataLair really works on real hardware. So we've implemented DataLair as a device mapper for the Linux kernel, and we have evaluated it on an SSD using Bonnie++ with ext4 file systems built on the logical volumes. The two metrics for our comparison were throughput and latency, and we compared with dmcrypt, which is a commonly used disk encryption tool, and Hive, which was the state of the art when this paper was published. And the main takeaway from this slide is that DataLair public read throughputs are 95 times faster than Hive because it's not affected by the ORAM overhead, while we have a logarithmic improvement for writes, both public and hidden, due to the better asymptotic complexity of DLORM. Latency will follow the same numbers, so I'll skip the slide here. And finally, to bridge the gap and to make public accesses more efficient, we propose two optimizations. One is to perform in-place public updates and performing hidden writes with only these public updates. And second is to delay hidden writes. And then it can be shown that DataLair achieves a maximum throughput of 32 megabytes per second, which is orders of magnitude faster than previous work and only a few times slower than a raw disk. Finally, I have some concluding remarks, which says that in this paper we show that it is possible to build efficient plausible deniability systems. However, we are still far away from a final solution which can replace simple encryption as the go-to standard tool. We still have to talk about usability, how usable these systems are, how much responsibility is on the users. And we have to talk about how these systems can be implemented, in which layer of the software can we implement this. Does this need to be a file system? Does this need to be on the device level? And how it can be integrated transparently with other software in the software stack. Finally, we also need to talk about the security and performance trade-off. We are considering write-only ORAMs here. Is that too strong for a real practical plausible deniability adversary? And whether it's customizable based on user parameters, how much sensitive information he really wants to store. So with that, I'll conclude my talk, and I'll be happy to take questions.